Hello everybody, my name is MD Rakibuzzaman and today I'm going to present my paper titled Layer to Layer Endurance Variation of 3D NAND Flash Memory. First, I would like to thank IRPS for giving me the opportunity to present in such a prestigious platform. I would also like to thank my co-authors for their support. This work has been funded by NSF and Alabama Ed School. Let's first talk about the motivation and background for this work. Flash memory is used to store data, and we are using flash memory every day in our day-to-day lives. In mobile phone, laptop, tablets, digital camera, thumb drives, automatic vehicles such as Tesla, data center, even in space, we are using flash memories to store data every now and then. One of the major reliability concerns for flash memory is its endurance. Endurance is defined by the number of program and erase cycle can take place before the flash memory become unreliable to store data for a longer time. To understand the importance of endurance for flash memory, we can take an example of the Tesla's recall on 2021. Tesla recalled more than 134,000 vehicles because of its flash memory failure, which resulted in a total of $286 million loss. So, NAND flash memory has a finite endurance, which is defined by the number of program and erase cycle, and my work focuses on characterization of endurance in 3D NAND flash memories. Now let's talk about the trends for data storage density in flash memory and their challenges. So the storage density of flash memory is increasing day by day, and flash memory has evolved from its planar 2D architecture to vertical 3D NAND architecture. The new scaling dimension for 3D NAND flash memory is its number of vertical layers. And continual advances in this technology promises an increasing number of vertical layers from its early 32 to contemporary 176 layers. And these advances promises to extend an incredible growth of bit density in next few decades. And it's reported that it will reach more than 1,000 layers by 2030. However, with the continual increases in layer number leads to higher number of pages per block, resulting large memory blocks. Managing these large size memory blocks in flash translation layer or FTL presents challenges for wire leveling of storage media. And this FTL wire leveling algorithm ensures that all the pages in a block share equal number of program erase or PE cycle. Since the maximum number of PE cycle a block can endure is determined by the weakest page within the block, the entire block is marked bad as soon as it detects one page can no longer ensure data integrity. This approach may lead to underutilization of storage resources, especially in the case where there is a significant endurance variation among pages. Hence, it is important to understand the variability among pages in 3D NAND flash memory for efficient utilization of its storage capacity. Here is the outline for my talk. First, I will briefly go through 3D NAND basic architecture. Then I will discuss about the experimental setup we have used to collect data for experimental results. Then I will show some experimental results on endurance variation among layers, root cause analysis for this variation and its validation. Finally, I will conclude the talk with some possible solutions. A NAND flash memory cell is a MOSFET transistor with floating gate or charge trap, which can trap charges and hold it even when the power is turned off. The floating gate is electrically isolated from the transistor terminal by its channel and gate oxides. This trapped negative charges increases the transistor threshold voltage, and when there is sufficient amount of charge stored in floating gate, we call it as a program state. When we remove all the charges from floating gate, we call it as a erase state. A repeated program erase involves the charges go back and forth from the floating gate, damaging the tunnel oxide. And then charge detrapping will take place because of this damage, and flash will no longer be available to hold charges for a long time, and the storage memory will be unreliable. So this tunnel oxide degradation limits the endurance for flash memory. So it is important to understand the vertical structure of 3D NAND array. 3D NAND flash memory has a layer architecture of alternate metal and insulating layers. The metal layers are shown in green colors, where the intermediate insulating layers are kept transparent. Each metal layer forms word lines of memory array connecting multiple memory cells. Then a channel of the memory cell is formed by creating holes that contain flash memory cells through the 3D structure with reactive ion etching process, which is shown in the yellow vertical pillars in second figure. Then the gate stack is formed sequentially by depositing blocking oxides, charge trap or floating gate. And finally, a thin layer of polysilicon channel is deposited with hollow core filled with oxide. The red pillars on the third figure on top are the bit lines through which we can control the voltages for different flash memory operations such as block erase, page program or page read operation. The high aspect ratio of ion etching makes the process inefficient at the bottom and gives a tapered shape architecture. So typically the cells in the bottom layers are lower in diameter, and this unique structure leads to sufficient layer to layer variation inside a flash memory block. Our experimental setup consists of 3D NAND flash memory, a standard T-sub socket that holds the memory, an interface device such as FTDI to act as a bridge between the computer interface and the flash memory chip. A software platform controls the flash memory chip and sends commands to send data or perform multiple flash memory operations such as block erase, page program or page read operation. For our experimental evaluations, we have used a multiple 3D MLC NAND flash memory with 32 layer and 1024 logical pages per block, each with 16 kilobyte in size. To understand the endurance variation among different layers as a function of array's wire level, we perform repeated program erase cycle on different blocks. The raw bit error rate collected right after the program operation may not represent the actual endurance status, as flash memory is expected to retain data for a long time. So for more realistic characterization, we perform accelerated data retention test by baking the chip at a higher temperature of 120 degrees Celsius up to 3 hours. We then perform read operations to determine the raw bit error rate for both fresh and program erase cycle block. In the figures, the x-axis represents the number of layers, the y-axis represents the raw bit error rate, Every point in this plot represents the of average raw bit error rate for all the pages located inside that layer. The different colors represents different baking times. From the left side figure, we can clearly see the layer to layer variability is minimal in fresh condition. Where on the right hand side figure, we can see there is a significant layer to layer variation. Especially the bottom layers are degrading faster than the other layers with program erase cycle. To understand the root cause of this variation, it is important to understand the erase operation. The erase operation happens on a block level in NAND flash memory. That means all the pages inside a block are erased together. The erase pulse is typically applied through the silicon substrate and the bit line, while all the word lines are grounded. The erase voltage gradually propagates into the vertical memory channel through top and bottom layers, and the pages on top and bottom layers see higher voltage and their oxides are stressed a bit more than the middle layers. Hence, the pages on the edge layers degrade faster than the pages on the middle layers. The degradation rate on the bottom layer are the highest due to the smaller diameter, which causes higher electric field in the gate oxide. So we postulate that the layer variation comes from the unique tapered shape architecture of 3D NAND flash memory, which fundamentally dictates the uneven erase depths among the layers. So to illustrate that further, we use the right hand side figure. After a program operation, the threshold voltage distribution for all the layers lie above the program verify level. The moment we apply an erase operation, we can see the erase depth on edge layers are higher than the middle layers. So to validate these hypotheses, I use a partial erase operation. So we are working on commercially available NAND flash memory. So the measuring of cell threshold voltage distribution was not available. So I came up with a new idea of verifying this by performing partial erase operation, where partial erase can be explained as we are stopping the block erase time at a time PE lower than its nominal time TE. On the right hand side plot, we are measuring the percentage of erase bits as a function of layer number, where each dot in this plot represents the average number of erase bits in all the pages located inside that layer number. The higher percentage of erase bit represents higher erase speed for that layer. And it is clear from this figure that edge layers are faster to erase. That validates our hypothesis that erase depth variation after a block erase operation dictates the layer to layer variation, layer to layer endurance variation inside a block. So in conclusion, a NAND flash memory block is marked bad as soon as it detects a page can no longer ensure data integrity. And we find that the pages located inside a NAND flash memory block shows a large amount of variations, and these variations are correlated to their page positions and are caused by uneven cell threshold voltage distribution after a block erase operation. So one weak page from the block can lead to a block to be discarded prematurely, leaving the storage capacity unutilized as shown in the red bars from the figure. So our findings suggest that a more sophisticated while labeling algorithm can be developed to utilize and counter this endurance variation. For example, we can develop a smart memory management in the flash translation layer, such as we discard the weak pages from the edge layers after a certain program erase cycle. This kind of intra-block word labeling is necessary for better utilization of storage capacity and enhance the endurance of 3D NAND flash memory. Thank you.